Yo cerca, sí, pues no lo veo. Yo es que la otra, el seminario que me acuerdo que no veía.
Recuerdo un poco de mi
No te voy a dejar nada. ¿Hasta no me lo puedo quitar?
Sí. Okay, so let's start. Today, our speaker is Fernando Buitrago. Most of you already know him, and he told me that I should stress that he's from Salamanca. So I think I'm properly doing the introduction like this. He did the master studies at IAC and the PhD in Nottingham. After that, he did postdocs positions in Edinburgh and Lisbon. And now he occupies a permanent position at the University of Valladolid. And today he's going to talk about the mass metallicity relation in galaxies and progressive demand. So,
Mass size.
Just a glitch. So whatever you want.
Thank you very much, Juan, for the introduction and for the invitation for this seminar. Just a couple of remarks. I have not permanent position yet. I'm still on track. And I also belong to the Instituto de Astrofísica y Ciencias do Espaço in Portugal. So yes, I want to introduce you today to the series of activities we are conducting in James Webb, which is my ministry project. And of course, it is not the work of a single person, it's the work of a large group of people. Among those, of course, Jesus, that is also part here in CEPCA. And today I'm going to stress everything about the masses relation and whether it is possible or not to assign physically motivated sizes to galaxies. This is going to be the main topic of the talk. I think that it is not necessary to give a broad introduction in CEPCA about galaxy evolution because most of you work on this topic. Just quick reminder, galaxies are the bricks that build our universe. And if we believe lambda CDM as our paradigm to galaxy formation and evolution, we live in a universe which is undergoing an accelerated expansion. And because we have cold dark matter, everything should be created in a bottom-up manner. So first proto-galaxies that little by little will be merging in a hierarchical universe. And at the end of the day, you will come up with the most massive galaxies of the universe as the final outcome of this process. At least this is what we believe at a face value. And of course, nowadays, we are very happy we have James Webb, we can reach even up to Redshift 15 or so. We are also in the first science of this telescope, both Jesus and I still don't control this very much. And you know, if you go to James Webb and you go up to those redshifts, you can see these tiny globes, which is the galaxy I was speaking about. Very exciting science, but sometimes we forget a crucial element, which is that, of course, we can observe these guys, but for galaxies which are more nearby, we can see an incredible amount of details of those. So even if you restrain yourself up to Redshift 1 or 2, with James Webb, you can see, as we say in Spanish, even the belly button of those galaxies. And this is the kind of work that we are trying to do. And specifically on this topic, I am working on something which is called the lossless brightness universe. Again, you have here Mohammed, you have here Raul, you have here Sepide, you have here a large amount of people who is speaking you about all these very extended structures on galaxies in which they are fuzzy, and it is not easy to pair those characteristics of galaxies, because with the standard images that we have from our universe, which is slow, what we can see is, well, it is very large amount of details in comparison to what we have, let's say, a couple of decades ago. But for example, I selected this image because here you can see the Stefan Quintet, which is this compact galaxy group that was observed. Well, it is very well known since many decades ago, but there is a very beautiful press release in James Webb about it. And here in these images, yes, you can see that several galaxies all together, but let's say nothing else. And the beautiful spiral galaxy on the top. The brightness, the limiting magnitude of this image, it's something like 26.5 magnitude per square second, whatever this number means. But if you go deeper, you can see this image. Of course. Well, now the limiting surface brightness is something like 28.5. And just by reaching 2 magnitudes deeper, you can see all the tidal streams in this galaxy compact group. You can see also the dust silver from our own galaxy. You can tell a lot of more structure in the spiral galaxy. And of course, all the systematics that you have in the group. And only reaching this time at 28.5. Remember that when Mohammed, Sepideh, or Raul give talks, they are able to tell you things even up to 31.5 magnitudes per square second. Could you imagine how the sky would look like at this depth? And the answer is that in few years' time, this is what we will see. With the Euclid satellite, that as you know is the new SIM mission, 1.2 space telescope, 1.2 meter telescope into space, we are going to have 2 cameras, the first one in the optical and the second one in the near infrared, that are going to observe 1/3 of the sky to surface brightness, something like the one that you are looking at here, or even a little bit deeper than this. So the cool thing, well, the main features is that in the optical, we are going to have a single filter. I'm going to try to use the mouse for the people which are at home. Hello, mouse. Well, there is no mouse. Okay, I will tell you with my voice. So the optical camera, it is going to be composed of a single filter which encompasses R, I, and Z Sloan filters. And in the near infrared, you are going to have Y, J, and H. For a spatial resolution, which is just about HST1. So I am telling you that we are going to have a very deep survey of the whole sky with an HST spatial resolution. And for 3 selected fields, we are going to have even 2 magnitudes deeper than that. This is going to be the state of the art in few years' time. And of course, we are conducting a lot of work in order to be able to reduce the images in such a way that we are going to retain all this extended structure. And it is very important to emphasize this aspect, because if you don't proceed this way, this information will be erased from those images. The paradigmatic case about that is the Hubble ultradeep field that, as you well know, is the deepest pointing with HST. Many of you will be familiar with this extreme deep field data release. This data rendition was focused on super high redshift galaxies, which at that time were redshift 10 or so. So for those guys that this did a study, the thing was that everything that was extended in the image was treated like noise, and therefore they trim out all the signal. And you can tell in this elliptical galaxy, which is a redshift 0.65 in the Hubble ultradeep field, they remove all the outer parts. And in my case, in Edinburgh, we tried to make a data rendition which was better than that, trying to maintain all the external parts, and you can tell that the galaxy looked like completely different. But better than that, our colleague Alex Borla was able to reduce all the HST data from scratch and was able to show this galaxy to its real beauty. And you can see that with the surface brightness profile. So the luminosity of the galaxy versus the galactocentric distance. The red line is what you could see with extreme DF. This is what we did in my 2017 paper. And in Alex images, he's able to reach 20 a second, or in other words, you cannot see it here, 140 kiloparsecs of this galaxy, which is a redshift 0.65. And this is the amount of information that we are going to have with you. So we need to get ready for this kind of revolution. I don't want to use the word revolution because I think that we are using too much now nowadays for proposals, etc. But I think it's the amount of galaxies that we are going to deal with and the amount of information that we are going to have per galaxy is going to exceed our craziest dream. The other way around. Yeah. So this is the footprint of what we are going to see with you. It's the part in green background, because in blue we have the zone of avoidance composed of the galaxy plane and the ecliptic. And all the individual green dots correspond to galaxies which are below redshift 0.3. So these are galaxies which are going to be ultra extended in our images, and for which we can capture all these super extended structures. But I was telling to you, it's not going to be only the local universe. We can go even up to redshift 0.5 or so in order to do this spot. So it's going to take for us several years to be able to process and to understand how we can extract all the information that we want from the site. And in orange, the orange arrays correspond to these three draining fields, which I was telling you, in which we are going to be interdependent with depths equivalent to the Hubble ultradeep field, in fact. So, I told you that the topic of this talk is going to be galaxy sizes. The problem when it comes to galaxy sizes is that it is an ill-defined problem, because how can you assign a size to something which is fast? In the real world, we have a chair, right? It is very easy to tell where the chair ends up. But with galaxies, if you go to simulations, here you can see all the substructure of those galaxies, because again, in a hierarchical universe, we believe that galaxies grow because of interaction with minor objects. In Sloan 26.5, orange color, you can see that you are only looking at the very central part of galaxies. Nowadays, we are only looking at the tip of the iceberg that galaxies are. But even with Euclid, we are going to have a look only of the most prominent tidal tails that these galaxies have. So this is a long-standing quest, trying to go deeper and deeper in order to better trace galaxy assembly. And in imaging, for example, I am showing you what we are, the comparison of what we are able to do with Sloan with the deepest images that we have nowadays with the Gran Telescopio Canarias. You can see that for this spiral galaxy, you are able to look at a lot of models of structure, about the stellar halo of this galaxy, and also many more galaxy satellites surrounding it. So this is what it has been promised to us, and this is what we are really looking at in the images. I really hope that you haven't seen that slide, because my point was the following. In the beginning of times, for measuring galaxy sizes, we were resorting to isofocal radial. But of course, if you integrate for longer time, you are seeing bigger and bigger galaxies. Okay. So the people then resorted to something which is called effective radius, which I suppose that you have heard about that. And it is the semi-major axis of the ellipse, which encompasses half of the light coming from the galaxy. And it is what it is written as RE in this image. The problem is the following. Just look at the image. Here it is written, this dwarf galaxy, the effective radius is 1. And for this other ultra diffuse galaxy, which is another kind of dwarf galaxy, it is 3 times bigger. But visually, this galaxy and this galaxy, to me, they look absolutely the same. It is even worse than that. If I compare it with the top galaxy, here it's 6, and this galaxy to me seems much bigger than the one on the bottom. And same goes for this elliptical galaxy. It is far larger than this and that. And the size is kind of comparable. Of course, it is bigger, but there is not such stark contrast between this and this in numbers. If you take the scale bar, 6. So 6 is approximately, so 2 times 6 is 14, right? So I move this to the center of the galaxy, and you're telling me that the total size of this object is this 12, 14 kiloparsecs. Okay, I can see that you have an unequivocous way of defining the galaxy size, but yeah, I think it is not very representative of the real size of the object. Having said that, I don't want to speak here about effective radii because all of us have worked with those a lot in the past. So for example, when Javi was cool, he was doing this kind of thing, you know, the famous Fernando Buitrago paper when they were able to measure the velocity dispersion of massive galaxies at high redshift. Or for example, Carlinhos, he was trying to link the increase of the size of the most massive galaxies of the universe with the merger rate of those objects. So the North remembers that at some point in the past you were a cool guy. and same for me, right? I worked a lot in my, well, I must say, even Elena was cool at that time. Right? She was not exactly working with effective radii, but she was working a lot with red nuggets galaxy population. The red nugget galaxy population are those galaxies, very massive, the most massive galaxies of the universe. When you look at those at redshift 3 or so, they were far smaller than nowadays. They are like big globular clusters. And then the thing is then if you want to evolve those galaxies into the massive elliptical galaxy that we witness in our nearby universe, you need to undergo through a lot of merging. And this is what we want to try to prove with the low surface brightness signal. For example, in this other paper that we created with the Hubble ultradeep field data, you can see the amount of mass that massive galaxies have between 10 and 50 kiloparsecs, comparing galaxies at very high redshift, these magenta points, with elliptical galaxies in the Hubble ultradeep field with the expectation at redshift 0 because of simulations. And what you can see is that little by little, massive galaxies are increasing their mass in the outskirts in order to match the elliptical galaxy that we see nowadays. And the funny thing is just few galaxies are able to survive untouched since very high redshift till nowadays. And this population of massive galaxies, which are red nuggets also in the local universe, are called the relic galaxies. So relic galaxies are galaxies which we know for sure that they haven't undergone any kind of merger or any kind of big star formation activity since that moment. So they are real counterparts of what we see in the high redshift universe. The problem is that if you look at them, they are featureless and they are extremely small, right? And we know that there are very, very few of those. You need to go, this is the number density, 10 to minus 6 cubic megaparsecs, which means that you need to survey a square of 100 megaparsecs times 100 megaparsecs times 100 megaparsecs in order to find one of those. So in our whole local universe, there must be just a single one of these objects. And we have found it. And I just want, to diverge a little bit, telling you a strange aspect that we have just published the last week about it. We cannot see any dark matter in this galaxy. So let me introduce you to NGC 1277, which is a galaxy that is located in the Perseus cluster. So we took 3D spectroscopy about this galaxy, and in the same field of view, we have a big elliptical galaxy and our target red nugget galaxy. You can see that this galaxy is very strange. It rotates like a massive spiral galaxy in comparison with the elliptical that you can see it doesn't have any rotation. And the velocity dispersion is like a big elliptical galaxy. You can see that it has a higher velocity dispersion than the other elliptical galaxy in the field. And the funny thing is that if you look at the cumulative mass profiles of those galaxies, the elliptical galaxy at the bottom is consistent with the typical elliptical galaxy, baryon dominated in the center, and then as you move to the outer parts, the baryonic matter increases, but the dark matter also increases. The dark matter is this solid black line. However, if you go to NGC 1277, the center is baryon dominated and actually with a very big supermassive black hole. And as you move to higher and higher galactocentric distances, there is no dark matter. This is what we find of dark matter in the system up to 20 kiloparsecs, something like 10 to 8 solar masses, almost nothing. Even if you extrapolate the profile up to say 200 kiloparsec, you are going to have something like 5 10 to 9 solar masses of dark matter in comparison with a stellar mass of something like 2 times 10 to 11 solar masses. So this is a conundrum for us. How is it possible? You know, there are tidal dwarf galaxies in which you can create a dwarf galaxy without any dark matter because of a merger interaction. This is well understood. It is not a problem for lambda CDM, etc. However, this galaxy, it's super mysterious. And the paper actually it's telling you, well, this is what we find. We don't have any idea what we are looking at. Anyway, that was just a small diversion. The point of this talk, again, it's speaking to you about galaxy sizes. So I was speaking about the effective radius. It is very good. That's why we use the high redshift universe, because perhaps it's the only way to measure the sizes of galaxies at high redshift, because it is very robust against the signal to noise of your galaxy. Because all this extended structure that I was telling you about doesn't contribute very much to the total light of the galaxy. So if you focus just on the part in which you are measuring half of the light from this galaxy, whether you integrate longer or shorter time, more or less you are going to get the same result. And it is a very easy to calculate number, because you sum up all the pixels from your galaxy and you get only, and at the end of the day, you restrain only to half of the sum of those pixels. However, it is a completely arbitrary size proxy. Why 50% of the galaxy light and not any other percentage, 20, 80% or so? Of course, it is not linked with our intuitive idea of a galaxy size, because for me, a galaxy size will be something like this or like this, right? And finally, it depends very much on the light concentration. Imagine that you have two galaxies with the same brightness. One is a pure disk and the other one has a bulge. Because of in the bulge, you are going to concentrate a lot of light. The effective radius of this later galaxy is going to be much smaller than the first one that was a bulgeless galaxy. Okay, so there are many things which we had always in our minds this idea that we can improve the state of the art about how to measure a size for a galaxy. But it was unclear how to do so until the moment of, well, I will come to that in a second. Our idea is to try to map the largest distance in which it was efficient to create stars. But my point was, we didn't know very much what to look at until the moment that we saw these profiles from our colleague, Cristina Martinez-Lombilla. So these are two H-on galaxies in which we observe in the ultraviolet, in the optical, and the near infrared. And the funny thing about these galaxy surface brightness profiles is that you can see that at certain radius, you have a sudden drop in the surface brightness profiles, regardless of the wavelength that you are looking at. So we started to think about that at that time, and we end up with, there was something measured in the late 70s, which was called galaxy truncations. So this person, Peter van der Kruijt, saw that for several H-on galaxies in his sample, no matter how much time he was integrating, he was always looking at the same galaxy sizes. It was kind of the termination of the galaxy disk. That's why we have this idea about, well, if you believe in the Schmidt law, and in order to create a star, you need to have a certain density of gas. all galaxies should not only have a certain size because of the moment in which all these in situ components of gas was able to create stars. And apart from that moment, or apart from that location, the gas density was not enough in order to create stars. So at least for galaxy disk, this should be very clear in our images. And we try to pursue this idea. So Nacho Trujillo compiled for several galaxies in the Sloan star 82, which is the deepest observation with the Sloan, the effective radius, the effective radii of galaxies in comparison with the radius in which these galaxies reach a stellar density of 1 solar mass per square parsec. That was roughly the moment in which this termination of the disk occurred. And as you can tell in the size mass relation, the scatter using the new galaxy size proxy was much smaller than in the case that we are using effective radial. So, when you are working on a scaling relation and suddenly the scatter decreases very much, it's because you are hitting something that regards with physics. So we try to pursue this idea a little bit. By the way, this is the effective radius, for example, of this galaxy, and this is the radius when you reach this 1 solar mass per square parsec density. But again, the problem is that if you resort to 1 solar mass per square parsec, you are doing the same mistake as with the effective radius, in the sense that why 1 solar mass are not any other value. So we committed to the idea of trying to look for these truncations in the surface brightness profiles of all galaxies in our samples. And we divided the task. Nusky and Chamba took galaxies in the local universe, and in my personal case, I took galaxies in the deepest points of HST in order to trace the evolution of this parameter of the way up to redshift 1. So what we were looking at were sudden drops in the surface brightness profiles of galaxies in the outer parts, which were at the same time accompanied of drops in the mass profile of the galaxies. And we also know that in the color profiles of galaxies, there are also changes. So we needed to look at several things for the same galaxy. And even in my personal case, because the spatial resolution of HST is worse, of course, than in the local universe, I didn't do ellipse profiles following the geometry of the galaxy, but I was also looking at just the semi-major axis. Because the problem is that when you are using elliptical apertures on the top of your galaxies, you are averaging the geometry of the different galaxy components. And if the disk is a little bit inclined and you have a pure spherical halo and a pure spherical bulge, you are mixing light. So sometimes you can see the signal more clear if you just follow the semi-major profile, the semi-major axis, in comparison if you do elliptical surface brightness profiles that we always do. So I am gonna tell you what we found in the high redshift sample, but using what Nuskia has studied as the reference in the local universe. I took over 1,000 galaxies in the Cantor sphere that, as you well know, are the deepest observation in the HST, only focusing in this because in principle, from what I told you, these are the easiest case in which to pinpoint these truncations. Fairly massive galaxies in order to increase the signal to noise, spectroscopic redshift below 1 in order not to be killed by the cosmological dimming in our images. And finally, trying to remove from our sample everything that was interacting in order to make sure that this truncation feature was not erased. And here you can look how this new size proxy look like on the top of galaxies. The effective radius are the blue ellipses, right? The blue, in fact, the effective radius will be the radius of the whole ellipse. And the galaxy edge or galaxy truncation will be the semi-major axis of the golden ellipse. These are 6 Milky Way-like galaxies from redshift almost 0, redshift 0.2, 0.4, and so forth, all the way up to redshift 1. So this is how this look like in the deepest point in an HST And this is how the truncation trace the whole structure of those disks in HSD. If you want to quantify this, this is the new mass size relation. NuScale points in the local universe are the gray data points, which are fitted by this dashed line. And the color points correspond to our sample at high redshift. But this is not high, this is intermediate redshift, from redshift 0.2, 0.4, 0.6, etc., all the way up to redshift. And the color points are colored by the stellar mass density at the truncation position. And more about this parameter in a second. The interesting thing about this is that we recover the same statistical tendency as with effective radii, meaning that as you move progressively to higher redshift, galaxies are getting smaller and smaller. And this other parameter I was speaking to you about, the stellar density at the truncation position increases with redshift. Meaning that in the local universe, this truncation most probably is going to be found at the 1 solar mass per square parsec, as Nacho was pointing out. But when you move to higher and higher redshift, you can tell that usually typical values that we found is 10 solar masses per square parsec, reflecting somehow the condition for forming stars at high redshift, right? Here you have a lot of stellar formation, you have a lot of supernovae, and then in order to have efficient star formation, you needed to have higher mass densities. At redshift 0, this is not the case, and even with smaller densities, you are able to efficiently form stars. And this time we are called about the our truncation position, right? So galaxies which are smaller have even higher stellar densities at this position. To be honest with you, people, I am a little bit nervous today, and the problem is that I'm in front of an audience for which I know most of you, and I want to do things well. Anyways, this is the money plot of the paper. In the x-axis, redshift, and in the y-axis, you have the truncation position, and in green, you have the stellar density at the truncation position. So according to this new size proxy, galaxies decrease, or these galaxies decrease their sizes by a factor of 2, all the way down to redshift 1. And at the same time, the stellar surface at the truncation position, the density of the disk, increases by over an order of magnitude. And we wanted to parameterize how the size evolution was taking place. So we compare the result, the published results for effective radii in comparison with what we see with galaxy edges, parameterizing everything according to the Hubble parameter or 1 plus x, the inverse of the scale. And the funny thing about that is it's two things. First of all, that you can see that the tendency of decreasing is much weaker by using galaxy edges or truncation than by using effective radii. And at the top of that, the evolution goes as 1 plus x to the minus 1 power. Exactly minus 1. And this makes also wonder whether there is some more interesting science we have behind of that. The idea is at some point to try to link the size evolution of dark matter halos with what we see in baryonic matter. And we are undergoing some simulations with Claudio de la Vecchia about that. Because if you go to the theoretical expectation many years ago by Moore, White, etc., they are telling you that if you join a characteristic parameter for the sizes of the baryonic matter with angular momentum, you can get the sizes and the masses of dark matter halos. And this is going to be the second step for our study. Not really, because the real second step of our study is to try to do that for very large number of galaxies. So far, we have measured this only for 1,000 galaxies in the local universe. This is the work by NuScale, and 1,000 galaxies in the intermediate redshift universe, and this is the work by me. We need to enlarge our samples, and at some point to link this with the dark matter evolution. And this is what my PhD student at the University of Valladolid, Jesus Fernández, is doing. You can tell that this is a pattern recognition problem because you need to look at the surface brightness of galaxies, the mass images, the mass density of the galaxies, and the color profiles of these galaxies. So you need to link several pieces. And he's using units armed with convolutional neural networks in order at the end of the day to return to us something like this clever segmentation of where the sizes of the galaxies are. And he's using a specific metric called DAX. An image is always worth 1,000 words, so I will prefer to show you the results. So we want to compare why our study about the galaxy's truncation returned to us with the outputs of the neural networks. Okay, so this is what you have just seen before. The ellipse in which the semi-major axis was the truncation radius. This is the label that we are feeding to our neural networks. This is what we call the A, okay? And this is what the neural network is returning to us as where the truncation of the galaxy is. This is what we call the chestnut. Why is that so bad? Because this corresponds to the famous Spanish idioms. Esto se parece como un huevo en la pestaña. Well, so because in the beginning nothing was the yellow pixels are those that correspond to the galaxy, and the purple pixels are those that correspond to the pattern. And this is what we are trying to match with the dice coefficient. Why? Because this is a very unbalanced problem. You can see that there are a lot of background pixels, and we cannot use just a normal accuracy. And the same goes if you want to use the purity of the completeness. Because in the purity, if you just mark a single pixel as galaxy, you have 100%. In completeness, if everything is a galaxy for you, also you have 100% of accuracy. So you use the harmonic mean of the both purity and completeness. And this is the dice coefficient. So you have here 3 galaxies. These are our labels coming from the paper of the galaxy sizes. This is the outputs of our neural networks, and this is how they match the 2 of them with the galaxies I was showing to you before. So you can tell that the machine is doing a pretty good job, as our metric tells. And well, the thing is, this is the first time in which transversal science has worked. All my people in computer science don't know anything about galaxies, and I don't know anything or almost anything about neural networks, right? So we invented many ways to work with our data. So we feed the neural networks with RGB images, with mass images, with color images of all different kinds. And we use, and these are the different inputs that we gave, and we use different architectures. And by doing so, we are obtaining different numbers for the metric. And through a mathematical process, we are sure that this is telling us that all of our different possibilities of inputs and neural networks and architecture for neural networks are learning in a different way. And the good thing about that is that in that case, you can finally combine the results of all the different neural networks. More about this in a second. This is very good, but again, this is 1,000 galaxies. I suppose that Jesus at some point will need to face even more than those. But for using millions and even billions of galaxies, the person who is going to have the final answer is Jesus. So, as I was telling you, when you use just a single neural network, you obtain an acceptable result. Same goes if you use different neural networks. But when you combine democratically those, you are obtaining even better results. So for every pixel in this image, every neural network has both, whether it belongs or it doesn't belong. It doesn't belong to the galaxy. And the results are better by combining neural networks than by using individual ones. You can see how this compares with the ground truth. And I can tell you that 2/3 of the combination provide us with better final results than our best performance individual case. And the data that it is more interesting for our neural networks is the mass maps of the galaxy. It's combining the mass maps with the surface brightness. The same as for astronomers, because an astronomer, in order to locate the truncation, needs to look at the sudden drop in the surface brightness profiles, but also how this matches with the mass profiles of galaxies. So apparently, the neural network is doing things the same way as the human operator. We are very happy about these results. And with my other PhD students, Samanel Radii, what we are trying to do is to understand the real nature of why these truncations are taking place. And actually, one step beyond that, in the sense that perhaps the truncation, it is very clear in a certain part of the galaxy, but in other part of the galaxy, you are growing a spiral arm, you are going to have an interaction, etc., and the things are more diffuse. So this idea of giving you just a single number for the truncation value of the galaxy might be a fallacy. Different angular parts might have different borders, which again makes sense. Or it's the same idea as Carlenius always have about, let's not give just a single value for the redshift of a galaxy. A PDF is always going to be more powerful for just a single value. So same thing, but using galaxy colors and using surface brightness. And of course, this is with the images that we have nowadays. When we were able to play with James Webb, things are going to be even better. They laugh a lot about me when I say in James Webb, I want to use galaxies up to redshift 1 or 2. But you can tell that, for example, for this spiral galaxy, this is what you look in HST, and this is what you see in. This is the projection of the 2D surface brightness profile in HST and in James Webb. This is HST resolution. You can see the bulge. Then you have kind of a bar, and you have the disk with the truncation here and here. But with 3 times greater spatial resolution, you can tell that here you have an spiral arms, which is growing, and that's why this part is more diffuse. But in the northern part of the galaxy, the truncation is much clearer. So I'm going to end up my presentation here. You can tell that those surface brightness is going to be very cool, not only for dwarf, very faint galaxies, but also for massive galaxies. We are going to be able to trace the assembly and the borders of those galaxies. And when speaking about galaxy sizes, Milky Way galaxies decrease their size by a factor of 2 in redshift 1, and you can parameterize this as an evolution as 1 plus f to the minus 1 power. While at the same time, their mass density increases by an order of magnitude. And by using not only standard algorithms, but using neural networks, so we want to expand our sample and to really understand how all these processes are taking place for the dark matter, as I told you, and also for the baryonic matter. Because in the very near future, we are going to have this kind of information for the whole sky with surface brightness limit of the deepest observation that we have nowadays for the whole sky. And for selected zones, we are going to have same depth as the Hubble ultradeep field. So the future is going to be really bright for us. Thank you very much.
Thank you very much. A very nice talk. Question? Yes.
Oh, I have a couple of them. So first of all, thank you very much. Very nice talk. I'm assuming this method only works with these galaxies, right?
No, Nuskia has used all kinds of morphological types. But the problem is it is much difficult to show that, for example, in elliptical galaxies, which you can see they are created out of accretion. So sometimes this picture is erased.
Exactly. And then my second question was whether you have tried to compare these measurements to other measurements that come from dynamical analysis, for example, the Vega-Ferrero or something like this. Something that is intrinsically related to the mass content of the galaxy, not just the distribution of the stars.
So as I told you, with the simulations of Claudio, we are going to try to look into that. I haven't done it yet, but yes, virial radius has to do with dark matter. So it may or may not exactly link with what we see in the values. Our final idea is to link the two, but so far we haven't done any real work into it, or any kind of work I can show you with a quantification. And you know that at some point I would like to do the same, not only with integrated light, but also trying to link result stellar populations with what we see in our images. That's why this idea I told you about the Stefan quintet.
Thanks.
Thank you, Fernando. Very nice talk. I was wondering, when you make the table with the different results for the different architectures and data sets you use, the difference seems very, very small. No? It seems to be quite constant, which is a result that I also obtained for the tidal feature detection. But when you show the plot that the mass is maybe the one which is performing better, how do you compute those mass profiles? You have to do some assumptions about the star populations, right?
A little bit. So for the mass profiles, we resort to the recipes in Rodiger and Puchot 2015, in which you need the surface brightness plus the galaxy color. And with that, you obtain for at every step in distance, you get a different mass to light ratio, which then you use in order to create the mass of the mass map of the galaxy. So let's say that you can do this in a pixel by pixel way. Problem is that, okay, it is good in the sense that you are not using a whole mass to light ratio for the whole galaxy, but it is not as a specific or detailed analysis as you will do, for example, with SCD analysis. Because again, everything is based on a color.
And so the ingredients would be the same as feeding the neural network with just light and colors, and the results are not the same.
I didn't understand it.
So to get your mass, you combine colors with light. So would you get exactly the same result if you input two maps, colors and light, rather than one single map, which is mass?
No, we have tried all the different combinations. By the way, I think I should also give a word at the end of the presentation about what we are doing these days in the world, right? Because we are going to be your neighbors for the rest of the week.
I think it's at the very end of the talk.
Yes, and I have mouse. Yeah, here. Just using RGB images, using all possible RGB images, using surface RGB image plus mass, using RGB image plus color, and using RGB images plus Sloan images, Sloan equivalent images of those galaxies. So we have used all possible combination with all possible of architecture as encoders. And what it gives you the best results is not just color, it is using the mass. Actually, using all possible of RGB images and using all possible of color images are kind of good, but the best one is when you also use mass.
Yeah. Although the difference is really, really small. It's one.
The difference is 1%, but the thing it is kind of appreciable. And it is not published yet because we are trying to improve things a little bit more before that, but it is almost there. We hope to send it to the journal next week. And all these things I was showing you about the truncation, we have already a referee report. It is kind of a good one. So I really hope that you're going to look at it very soon in the
More questions?
Can you please show the plot where you compare the standard effective radii with the new one? You call it R1 or what's the name of the new?
No, R1 was in the case of using just one solar mass per square parsec.
Uh-huh.
So at that time, it was what nature was measuring, and it corresponds to what you're looking at here.
Okay.
That in the case of the local universe are the gray points, and for galaxies in this plot, you can see that they are more or less purple-ish. So purple-ish
It's wrong one.
one solar mass per square parsec. Yeah, but at least for the local universe, this proxy was what I am telling you is that this threshold in mass density evolves with density.
Uh-huh.
But this is acceptable as redshift.
So I am very impressed with this plot. Provided that you have decreased the scatter, as you said, would you dare to establish an empirical relationship or something like that in a way that people working or having already obtained the effective radial can just extrapolate the new value? So just jumping all the real work and doing just an extrapolation. Do you think that might work, or is just too speculative?
There is a tendency. Actually, I think that it might be computed in the paper. I can remember it at the top of my head. Same as in my paper, right? Because it's the same tendency. In the two masses relation, we are looking at the same tendency. Smaller and smaller redshift goes right. So yes, there is kind of a proportionality between, in a statistical trend, but in a galaxy by galaxy basis, it is not the case.
Mm-hmm.
And you can tell very well here, right? So you can see that there is a clear decrease of the truncation position as redshift goes by, right? So the orange ellipses are always smaller and smaller.
Mm.
Do you agree with me on that?
Yep.
However, you can tell that the blue ellipses for the 6 cases are approximately the same. And this is the point. When you're using effective radii, you are always biased to how the light is concentrated. It is completely different when you have a prominent bulge or not.
Inclination as well.
Again, this is very good when you are able to trace whole extension of the galaxy, because at some point you see this change of the slope in the surface lines profiles. However, you have to imagine that could you see these vertical lines? This corresponds to the limited surface brightness of the images in our survey. As you go to higher and higher redshift, because of cosmological dimming, it's like your profiles, the normalization is going down and down. So at some point, the surface brightness of your images is going to be above the truncation range. So you can't see anything. And apart from redshift, as I told you, 1 or 2, this is completely game over. So effective radii is the best thing that we can do at high redshift.
Mm-hmm.
However, we know that it is a bias size proxy.
More questions? This is not a question. This is just that I like being speculative. So, do you have any personal opinion on what could be happening on this weird ass galaxy that you showed us before? Like the fact that it doesn't have dark matter and that all the mass concentrates in the center. Do you think that could be related to the fact that this galaxy has not interacted with anything in its entire life? Because this was one of the conditions, right? The red nuggets. Because this, I don't know, also remind me a bit to globular clusters.
They are kind of big globular clusters.
Yes, exactly. So I don't know. Do you have any like?
We have spoken these days a lot of what's going on with the people from simulations. So the idea is perhaps is that these are the first galaxies that are being formed as easy as that. So you have kind of a monolithic light collapse of gas.
Mm-hmm.
And because of you have so much energy released via supernovas at that time, you can be able to strip somehow the initial dark matter halo of those galaxies. And without dark matter, for example, you wouldn't have any tidal friction. And for this galaxy, it will be completely impossible to accrete anything. It is sitting in a galaxy cluster, but it is not able to see anything around. That might be a possibility. Also, the idea is if you have two dark matter halos containing just gas very early on, and the relative velocities are very different, they clash. You have a very big starburst. The two dark matter halos go away, and you have, in the middle of the interaction, you have this very compact remnant, kind of a mini Baller cluster in a galaxy scale. Everything is super speculative. The idea, what I'm trying to pursue these days in my free time, when Ricardo allows me not to work in clusters, is that, well, if these galaxies are consistent with just a very big starburst, and since then nothing happened, they are the galaxies in which the truncation must be the sharpest. So I am using the images of this NGC 1277, and I am trying to locate the truncation for that galaxy.
What about black hole having accreted only the dark matter?
I was thinking on that.
Well, the supermassive black hole of that galaxy is super special because you have to imagine that 1/100th of the stellar mass of the galaxy is concentrated in the supermassive black hole in the center. The galaxy is 10 to 11 solar masses, 2 times 10 to 11 solar masses, and the supermassive black hole is 10 times 10 to 9 or 10 to 10 solar masses. It's what the people have called a supermassive black hole, or even beyond supermassive black hole. Apart from that, this galaxy only has red globular clusters. This galaxy has a very bottom-up IMF at all radii. This galaxy is entire mystery for us, and we have now the following dilemma: Did we find a 10 sigma fluctuation, or is it something normal and there are more of these galaxies surrounding us, perhaps in the interior of the elliptical galaxies, and that's why we have missed those, and this is the first time that we are looking at something which is consistent with no dark matter. Done.
And just a comment, because there was a recent paper about void galaxies, or galaxies living in a void. Is there a room for these weird objects to be just living in voids? Because I agree with you that living in a cluster can be a condition to just being isolated, even if it's counterintuitive. But what about galaxies in voids?
This galaxy
Is not in a void.
is sitting in Perseus cluster,
Okay.
in a very big massive cluster. Actually, as you can tell, it is the satellite of another elliptical galaxy. Having said that, in our 2018 paper, we have seen that distance, group mass, yes. So all these color data points are these red galaxies. Okay, the colors correspond to whether they are more disk-like or more spheroid-like. You can see that 1/3 of our sample, let's say, live in kind of a group environment or something like that, not in clusters. So it seems that you have two channels of formation. Some of them, most of them live in galaxy clusters, but also some of them live more in a more isolated environment. We are at the stage, people, where we don't understand anything that is going on with these red galaxies. The funny thing is that they are super abundant at high redshift, but nowadays we have to play just with a bunch of them. Antonio, sorry.
What is the iron abundance of the galaxy? It would be very low.
Okay, for NGC 1277, I can show you a spectra with a super high quality at all radii of the galaxy. So we can have a better look about it. They are super metallic and they are very much at my face, especially on the center. For the rest of the galaxy, we just have a Sloan spectrum. So we have just to play with a couple of indices, but everything is consistent with that scenario. For this very galaxy I'm showing to you here, we have 10-hour spectra with X shooter, and I'm playing with it with Ignacio Ferreras. But again, we are respecting the same idea. Very metallic, very alpha haze, and consistent with a lot of AI.
One last question about the truncation. So if I understood well, the truncation appears because of the increase in the turbulence in the disk, no? So at low redshift, you have less turbulent disk. I mean, you can form stars and have the truncation at lower mass values. And then high redshift, that truncation increases because the disk is more turbulent.
Yeah, somehow. Yeah.
So that means that in gas, for example, in H1, those disks should not be truncated if it's a matter of turbulence and collapse of the gas. Do you know if there is an evolution, the size of the H1 distribution?
That will be a natural step, trying to see these things in H1 or in HR. Well, in HR, if it's related somehow with the star formation, there must be a correlation, right? Don't really know whether it should be or not a truncation in H1, in the sense that the idea is you need a certain threshold in mass density in order to create your stars. But the mass density might be also a continuum.
Yeah, I mean, just
expectation,
to distinguish if it's a matter of turbulence and collapse, or if there is really a truncation.
When we are speaking about density, we are speaking about the stellar density.
Mm.
Trying to somehow connect the density of the stars with density of gas.
This is the last question.
So again, perhaps I should be a little more cautious with this and to say that this might be a very nice way of going forward. Having said that, you know this idea that when we study extragalactic astronomy, they always told us, galaxies are much more extended in gas or in H1 than when you look at the optical. When looking at the low surface Radial structure of the galaxies, this might not be the case. The problem is that so far we have seen just with the slow and depth our universe. But when you go to deeper and deeper surface Radial limits, it might be the case that the galaxy extent is the same one in stars with optical light as with H1.
Okay, thank you very much.
We are going to be around for the rest of the week because we have a collaboration in order to identify cluster membership using machine learning. So you will see us around. The team is Jesus, Elena, Ricardo, Ana, and Irene. So looking forward to have a coffee with you at some point.
Yeah, even people are welcome for lunch. We will be having lunch.